Hey everyone, as you can see, I got a haircut. It's pretty awesome. My wife was upset with how I was looking, and she dragged me to the barber yesterday, and now I look fly as hell. And how that ties to what we're doing today is it doesn't tie in at all. I just wanted to share that I look fly right now. Could be better if I actually did my hair, but whatever. Um, so like I said in the previous video, Um, I am going to hold. What's going on over here? Okay, yeah. Sorry, just making sure the audio capture was happening. Um, I'm gonna put a little bit of space between myself and doing a proper householder reflections video, which will be lesson 11 now that I understand it and what that is. So, right now, today, I'm just gonna like focus on QR factorizations. I was trying to understand the implicit QR factorization method, but I think what I realized was, and I realized this with householder reflectors on this whole process as well, is this the implicit QR way is one way to QR factorize. So I just want to understand what exactly QR factorization was. So and this is like a little prompt trick as well. I'm just gonna read through this basically. That's essentially going to be this video is just like a recap of what QR factorizations are. But a neat little prompt trick is here, please explain in detail. And then in parentheses, I wrote, give me formal definitions, but also explain what every part of it means explicitly, not assuming much knowledge of matrices to begin with. Also, don't give me any code. The don't give me any code, we've already established why, because we're trying to actually code this up. So I just want to understand this. And what I liked about this strategy was that it still like gave me all the mathematical symbols, but it actually does pretty well about like explaining things deeper than that, right? Rather than just being like, here's all the math and like go ahead and understand. And then I have to like follow up prompt it and like instead try to get it to right on my level. Not that I don't know anything about matrices, but sometimes there's things just like I think with linear algebra and stats are both kind of weak points, which is sad as a data scientist. But in both of those cases, I feel like an issue I have is that some things I know computationally, as in like you just compute it, but intellectually, like abstractly, what does this mean? Why is it useful? Where can we, et cetera, et cetera. Those are the things that are missing, and sometimes getting that background knowledge of what this means in a simpler, like basic way, uh, actually helps me understand it better. Right? And someday we'll get to the point where I can just read a complicated equation and be like, oh yeah, this is what this means. But that day is not today. And to get there someday, I got to do the work today. That's just how life is, right? To get anywhere at any time, you need to start working on it today. So anyways, so QR factorization, also known as QR decomposition, is a way of breaking down or factoring a matrix into simpler matrices that captures its directional and that captures its scalings, right? So Q is the directions, the uh, matrix of orthonormal basis vectors, and then R is our scalings vector. And the reason you want an upper triangular is like to the first column in the upper triangular, right? Because you'll do like this, right? It will apply to each of the rows in Q, right? So each of the column, once the multiplication is complete or the transformation is complete, the first vector of R applies to all of the vectors on Q. The second applies from the second vector onwards, and so on and so forth, right? Which kind of reflects how basis vectors are built up one by one, like we did in the Gram-Schmidt process. Um, so this went super basic and I was just explaining what a matrix is, so I'm not going to read that. What does factorization mean in this particular case? It's essentially breaking down A into two separate matrices. And the formal definition is that um, if A is a full rank matrix, aka all of its columns are linearly independent, which requires m greater than n, means it has to have more rows than columns, which makes sense because if you were to write out a linear system of equations, it'll turn into a square matrix and uh, some vector x and then equals b, which is your output, right? So the reason that is because essentially a square matrix is where the number of equations matches the number of unknowns. So therefore, m needs to equal that or be greater. You could have more equations than you have unknowns, right? Um, which is okay. Um, so Q is an m by n matrix in which each column is uh, length 1 and the columns are each perpendicular to each other, meaning Q is a matrix of orthonormal vectors. R is an upper triangular matrix, which is square, and all entries below the main diagonal are 0. Um, and also, for some reason, we often require the diagonal entries to be positive to make the factorization unique. I don't understand that per se. And I'm having a bad day in the sense of I'm super sick. Well, not sick. I'm just like exhausted for some reason. Like, spoiler alert. If you've seen any of my previous videos, you know that that's actually a very common problem. But I'm just going to keep going down here. Um, so the Q matrix has orthonormal columns, meaning that they're orthogonal and normalized. Orthogonal, they're perpendicular to each other. Normalized, they're all unit length 1. Pretty straightforward. And because they're orthonormal, Q times Q transpose equals the identity matrix, which also means that the transpose of Q is equal to the inverse of Q, which is another thing that's not mentioned here, but it's true. I'm just going to actually confirm that. Does this also mean that Q, that the transpose of Q is the inverse also? Uh, when Q is square matrix with orthonormal is transpose is inverse. Okay, so yes, I was accurate on that. um, so that's Q. Um, and why orthonormal? Orthonormal vectors form the simplest possible axes in space. Um, and they behave like standard axes essentially. Like this is something I kind of intuited upon several episodes ago at this point, which was it's nice to know that something like you just kind of intuit and then you see the formalization of it and you're like, oh wow, I thought of that. That's fun, right? That's another thing. Like, you know, don't take anything for granted when you're learning. Like, just ask why for everything. Like, be like a child about it. Like, why? Except don't be like a child in the sense, at a certain point, a child realizes that they're just being annoying and they continue to be annoying. Don't do that. I'm particularly familiar with that because my niece and nephew are visiting right now. But yeah. Um, and then the R matrix is upper triangular, meaning that all entries below the diagonal are 0. Um, and why is it triangular? Making R triangular imposes a simple hierarchy where the first orthonormal direction Q1, aka the first vector in Q, explains part of every column. The second direction Q2, sorry, not the vectors in Q, the vectors in R, I think is what it's trying to say. I don't know why it's saying Q. Only explains the remainder of columns, etc., etc. The sequential structure matches the way we often build an orthonormal basis one vector at a time. So interpreting A equals QR, A equals and Q equals this, then for any element A equals R1 JQ1 plus R2 J. So it's just like expanding what each element actually becomes when you do that full matrix multiplication of QR. Um, The geometric interpretation being that Q spans the same subspace as A, but it's just the basis vectors, and R kind of showcases the scaling, essentially. Um, and then essentially, I mean, it's very straightforward. QR, you do that multiplication, you get A, no problem. Um, Connections to the Gram-Schmidt process. We've already done the Gram-Schmidt process, but essentially, and this is where I started realizing, like, okay, I'm not thinking about this right, because I noticed this a couple of other pages that I looked up. Essentially, is like finding eigenvalues and eigenvectors. That's just a truth, and like the way we were doing it is a method to get eigenvalues and eigenvectors with certain conditions. It's not the only way, right? Um, so doing the householder reflections and all that, that works with a symmetric matrix, but it doesn't work always, right? Um, Anyways, so we're not going to get into what the Gram-Schmidt process is because we've already talked about that. Any full existence and uniqueness, any full column rank matrix A, aka they have all the nearly independent columns, admits a QR factorization uniqueness. If we insist that each diagonal entry RII of R be positive, then the decomposition A equals QR is unique. Um, I'm assuming that means that if the diagonals are always positive of R, then A equals QR is always, there's only one A equals QR. Not really sure about that understanding wise, but I believe it. Uh, if key properties and applications, if A is squared and invertible, M equals N, then AX equals B, G equals QRX equals B, which means Rx equals Q transpose B. And solving a triangular system Rx equals Q transpose B is straightforward. Why? Why is this straightforward? I'm not sure why this is straightforward, but I believe it. Least squares problem for overdetermined systems where m is greater than n. The best solution to ax b is the Euclidean sense satisfies in the Euclidean sense satisfies Rx equals Q transpose B. Again, only one needs to solve an upper triangular system. Eigenvalue algorithms. The QR algorithm repeatedly factors a matrix into Q and R and then forms RQ. This iteration converges to a nearly triangular form revealing eigenvalues. Okay. Orthogonal transforms. Multiplying by Q preserves vector lengths and angles, which helps avoid amplifying rounding errors. Okay, and that's this little summary document I created. I'm gonna go into this in more detail later on, but today, guys, I gotta tap out. I'm sorry. It was a pleasure having you guys here, all two or three of you, or probably none. Have a great one. Thank you so much.